I'm going to talk to you about the LSP, the Large Scale Polarization Explorer, which is basic definition project, and mainly Italian project, devoted to the measurement of the polarization of the CMB at large angular scales, so between L equal about 3 and 200, with a not very high angular resolution of about 1.5 degrees. And the idea is to use it to detect, or put upper limits to the B mode at the reionization and recombination peaks. It's composed by two very different, actually, instruments. One is Lspe SWIPE, which is a spinning stratospheric balloon payload. So this is flying on a balloon and is flying a long duration in the polar night in the Arctic. So the idea is to fly it, from the North Pole for a long duration balloon during the night, and this allows to observe a very large fraction of the sky, thanks to the the fact that there is no solar illumination, and in a very stable and, I must say, cold environment. And it has a SWIPE as a polarization modulator based on a spinning alpha plate to reduce systematic effects, and about 330 TS multimodal detectors developed by INFN in Italy. SLEEP, instead, Lspe SLEEP is ground-based, lower frequency, I will say about frequency later, lower frequency radiometer-based instrument, and it's designed for deep characterization of the low frequency foregrounds, so mainly synchrotron. And it will be installed in Teide Observatory in Tenerife. The PI is are Paolo De Bernardis for SWIPE, Marco Bersanelli in Milano for SLEEP, and Flavio Gatti, INFN of Genoa, for development of the detectors. Let's see. Oops. Yeah, this is the collaboration, which is quite wide, and I may be missing some institutes, but that's more or less the collaboration, which is mainly Italian, Sapienza University and University of Milan and INFN, but we have many colleagues from abroad. Let me talk a moment about the observation strategy. So we have two different instruments, as I said. One is SLEEP, located in Tenerife, and it is, looking, the basic idea is similar to what John Jed discussed about Lightbird. So we have a precession angle, which is basically given by the co-latitude, and a zenith angle, which is what in the case of Lightbird is the spin angle. So with this strategy, with a small zenith angle, SLEEP can cover a strip of sky similar to the big circle dashed here. While Lspe, being orbiting around the pole, which with a much smaller precession angle, so a much smaller co-latitude, will observe at a lower angle above at a higher zenith angle, so a lower angle above the horizon, about 45 degrees, and observing again a wide strip of sky. And this is the situation for what concerns the coverage of the two instruments. So in blue, you can see the strip coverage, which of course it depends on the strategy of of the zenith angle strategy we adopt. This is one case. Which is studied to maximize overlap. And in yellow, you can see the SWIPE coverage from the balloon. And you can see that the green overlap region is quite so here are the basic instrumental parameters. So we have the frequencies, which we observe that are 45 gigahertz and 95 gigahertz for the low frequency instrument for SLEEP, and 145, 210, and 240 for the balloon for SWIPE. we have an angular resolution, as I say, not very small, so it's about 20 Earth minutes and 10 Earth minutes for sweep, and 1.5 degrees for swipe. The detector technology is different. We have radiometers in sweep, and we have multi-mode TSs. I will come back to this later for swipe. The number of polarimeters or detectors, it ranges from a very small number at 95 gigahertz to 49 at 43 gigahertz. And for the TS-based instrument, we have 162 to our main CMB channel, which is 145 gigahertz, and then 82 and 82 at 210 and 240 to monitor the behavior of dust, basically, in this part of the spectrum. The sensitivity, the NET for the single sensor is you see the numbers here. It's very high for swipe, so it's very small numbers, say for swipe, thanks to the multi-moded technology, which is collecting a lot of radiation. The observing time is 2 years for sweep from the ground, and 15 days for swipe from the balloon, with timing at 50% observing efficiency for sweep and about 90% for swipe. The sky coverage, we have seen it before, but basically it's 50% of the sky with sweep and 30% of the sky with swipe, with a common overlapping region, removing the galaxy of about 25% of the sky, so quite a large fraction of the sky. The map sensitivity is, you see the numbers here in terms of microkelvin CMB arc minutes, and it goes to a very small number for the 145 gigahertz channel. And this is computed using this very simple equation. And the noise, so basically this one on top is the noise per pixel, while if we convert to noise in power spectrum, taking into account the fact that we are observing only 25% of the sky, we basically double the noise power spectrum for polarization down to up to those values. And the NET includes photon noise, without noise, thermal noise, and margins. Okay, let me say something about the instrumentation. This is the strip radiometer-based instrument. I don't think I have the time to go very much in the details, but basically this is a telescope which adopts the one which was the Clover telescope with some refurbishment, and it's spinning around the zenith angle with a constant, spinning around the zenith with a constant zenith angle in order to cover large rings of sky in a fast way. The operating principle of the radiometers allows slips to recover both Q and U from a single measurement, and this is a very useful feature. Let's see. Okay. Yeah. Okay. This is to show you some of the development status. Here is the design of the strip instrument. This is the cryostat. I hope you see my pointer. Now should be better. Here is the cryostat. Here is the horn-based focal plane. This is one platelet-based module. This is one orthomorph transducer inside, at the bottom of each horn, and then there is the polarimeter sensors. What is the status of the focal plane development? So the cryostat, all components are basically being completed. The instrument is now fully integrated with cryostat electronics, and instrument level test is started. For the moment, the warm testing of instrument electronics interfaces is ongoing remotely. So we have here, you can see the cryostat, you can see the focal plane, filters, electronics board, and so on. For what concerns the telescope, as I say, this is the what it was the Clover telescope. So I've been transported to Milan from Oxford, and now a structural analysis is ongoing to, you know, be sure that the system is stable enough for spinning the strategy. The design of the remaining interfaces is ongoing, and we are preparing a drone-based system for beam calibration. Here you can see a simulation, basically a ray tracing simulation of the focal plane, and here you can see again a simulation of the side lobes in which we have, this is a scan over one of the beam, symmetrized, so you can see the asymmetries, you know, from the left part to the right part. And in this plot, you can have, you can see the copolar and cross-polar views. The site, as I said, will be a 3D observatory hosted by the Instituto de Astrofisica de Canarias. And there is an agreement going on between INFN, University of Milano, and Instituto de Astrofisica de Canarias for installing the telescope. It's a preliminary design of the telescope cover, and this is ready for use. This is now. Let me switch to the balloon-based instrument. So as I said, this is 145, 220, 240 gigahertz. The frequency don't span very much because we want to use an halfway plate, a single halfway plate for the full system. So we need to keep the band not too spread to avoid problems. I mean, we need to have a wide band halfway plate. This is the basic design of the instrument. You see there are big cryostats suspended in the gondola, and which will contain the detectors, of course. And we have a big box containing the electronics and the battery system, because of course this is will fly in the night, as I said. So the ambient temperature will be -90 Celsius. There are no solar panels due to the fact that it's flying in the dark. So with a consumption of 370 watts and an energy for the full mission of about alpha gigajoule, we need about 500 kilograms of batteries to be kept possibly around 0 Celsius in order to maximize the battery efficiency. Those will be lithium batteries. And so we have developed an aerogel-based insulation, and that will be, I mean, the box will be kept warm by the electronics power itself at around 0 Celsius. Of course, winter ballooning in the Arctic is not an easy task for many reasons. And you can see a picture of a test launch of some equipment, including a battery system from Svalbard in 2017. And you can see it was snowing during the launch operations. And or here in the right, you can see what we have developed in order to make, you know, an assessment of the possibility to actually fly in the north. We have developed a simulator of trajectory based on historical data and based on simulations. And you can see that the trajectory, so every dot here is 1 day, and you can see that the trajectory is quite fast. So typically for a long duration balloon in the summer, you know, in 15 days, you have about 1 large ring around the pole, while here we have, you know, 1, 2, 3, 4 rings. So this is means that the situation is somehow much more chaotic because the wind is much higher. Still, we have periods of the year, of the winter, in which the trajectories are quite, you know, close around the pole, which are very good for this kind of activity. In the middle plot here, you can see as a function of the launch hypothetical launch date. This is in the past because we're using historical data. How much time we could have been in the dark and how much time in the sun. So when you see a white spot, this means 1 hour in the sun, and when you see a blue dot, it means 1 hour in the dark. So, and here below you can see basically the integral of the above sunny hours. So you can see that for a launch from Kiruna in season 2017-2018, we could have a quite large amount of launching date with less than 20% of solar illumination and a few days with less of 5% solar illumination. Similarly, this is for a launch from Longyearbyen in Svalbard, and you can see generally a better result, so less solar illumination with a good fraction of the time below 15%, and about a couple of weeks with less than, or 1 week with less than 10%. So this means that launching is possible, but it has to be planned with large care and using this predictor. Luckily, we have daily we have prediction of stratospheric winds available, so we can basically for every day we can predict the following 2 weeks of trajectory. So this is a very useful tool. And but we also have to keep in mind that looking at these plots, that the solar illumination is basically very, very probable. It's very, very probable. So this is the schematic of the SWIPE test-based instrument. So we have a low-pressure liquid helium cryostat with a 600 millimeters window on top here. The window actually is made of 2 windows. One is a removable window, which will be only used on the ground, and it will be open at balloon altitude to reduce background and to reduce the instrumental polarization that we will have when radiation is crossing a slab in a tilted angle. So we will have some instrumental polarization on the off-axis detectors, depending on the thickness of the window. So having a very thin window is useful. So we will open the window similar to what IBEX has done at balloon altitude. Then we have a cold spinning alpha plate, which is a very interesting device, which is similar to what will be developed for Lightbird, as we have heard. We have a single polypropylene cold lens. We have a wide grid polarizer and 0.3 Kelvin fridge and 2 curved focal planes hosting those horns which are collecting radiation, not single modal but multimodal. Let me say a few words about the polarization modulator unit. So the diameter is 500 millimeters. The base temperature, so the temperature where we connect to, is 1.6 Kelvin, and we have a requirement of a dissipation below 30 milliwatts and a rotation frequency of 30 rounds per minute, so half an hertz basically, and a total mass less than 25 kilograms. So this is has been developed with based on a superconductive magnetic bearing, which has some for which we have developed some fancy features like a capacitive sensor system to measure the temperature and the position, the levitation position of the plate without having to touch the plate itself. There is a paper about that. There is a clamp relay system, which it's a bistable clamp system, so it's we can clamp and lock the system for the launch, and we can unclamp and leave it open, free after the system is cold. So the magnetic field is freezing the alpha plate holding system in position. Again, this is a fancy feature. Then we have also developed a room temperature mockup based off standard bearings to test the dynamics of the rotation and to test the encoder for the readout of the position, which I will say more about that, is very critical. Okay, some observing parameter. So clearly the polarization modulation will be at 4 times the frequency of the output plate. The frequency of the output plate will be 0.5 Hertz. So the modulation will be at 2 Hertz. And this modulation frequency basically is limited by the detector time constant, which is about 30 milliseconds. Those are big detectors, so the time constant is large. So the modulation frequency sets also a limit in the scan speed, because we want to, be able to basically demodulate the signal faster than the scanning speed. So we have about the spinning period is about 8.6 minutes, and of course this requires a very. This can induce several systematic effects. I will talk about that. So this is a bit about the status. So this is the 2 focal planes under development. This is one single horn in the focal plane, but we have more of them. And we have, for each of the focal plane, we have 81 detectors at 145 gigahertz, 41 at 240, and 41 at 210 gigahertz. This is one, you see, 1 centimeter wide spider web absorber with a TS sensor. So this is a very large and delicate sensor. The advantage of the multimoded TS system and the multimoded radiation collection is that the sensitivity per device scales as the number of modes collected, the square root of the number of modes collected. So with those 326 detectors, we can collect about 8,800 modes, which is equivalent to a much more complex instrument. Of course, we pay that with a coarser angular resolution of about 1.5 degrees. And, but this is, again, a simple and cost-effective system to reduce the number of detectors. Okay, this plot, those plots show, okay, this is for strip. You can see the background brightness from the atmosphere, from the window, and from the CMB, and you can see the 2 bands. And on the right here, we see the 3 bands of swipe, and you can see again the atmosphere at balloon altitudes. You see it's much lower than on the ground. The atmosphere at balloon altitudes, the brightness of the CMB in red, which is basically the dominating effect, and the brightness of the window. This is only the thin window that will be left after opening the thick window. And here you see the number of collected modes as a function of frequency for the 3 bands. So you can see that, for the lower frequency, we collect about 10 modes. For the highest frequency, 20 and 30. This is the factor that we gain. In order to make, assessment of the performance, we have developed 2 instrument simulators for the 2 instruments. And so this is done to assess the sensitivity and the impact of systematic effect. Those are based on a similar philosophy. So instrument database, generation of pointing, convolution of the angular response, effect of the output plate in case we have, addition of noise and systematic effects, both additive, multiplicative, or correlated among detectors or in time. Then we have some filtering procedure, map making, and which provides 3x3 noise covariance for each observed pixel. Let me say something about systematic effect budget. So this is the case of STRIP. In the case of STRIP, we have, using the instrument simulator, we have defined those requirements divided in goals, or the best we can hope, and the requirement, which is a bit larger than that. And here is the impact in terms of angular power spectrum for compared to E modes and B modes. Of course, you have to keep in mind that SLEEP is devoted to monitoring the foregrounds, not really to detect the B modes. So we don't need to go to the accuracy of the B modes for that. For what concern swipe, instead, swipe instrument is the instrument that will be devoted to assessing, to measuring the B modes, or putting an upper limits. And again, we have a list of requirements, which I'm not going over all of them, but I will say something later about that. And we also have the expected B mode RMS from those requirements, obtaining using this simple formula. So with the simulator, we have computed the B mode Cisabel, and the RMS is basically the integral of the B mode Cisabel weighted by the B. For the halfway plate in particular, we have developed a quite sophisticated simulation in which we simulate a few effects combined, which are the uncertainty in the measurement of the halfway plate angle, where we have an expected precision with, Kalman filtering technique of very, very small, about 0.1 arcminute. This is the noise of the recovered angle. Then we can, of course, add an offset of the recovered angle, which may do to, several effects. And we're simulating this with 3 different levels. And then we also are simulating an effect which we haven't seen, studied very much, which is the instability of the halfway plate spin rate, or better, the limited knowledge of the instantaneous halfway plate spin rate. This is an effect which, as I will show you later, has an impact on large scales of the polarization. We have estimated this fluctuation of the halfway plate angular velocity in those ranges from 0 to 0.6 10 to the minus 5. This is a relative effect. And we expect to be able to measure, using this Kalman filtering technique on the dynamics of the halfway plate, a level of 210 to the minus 6. To give some more information, we modeled in the production of the time ordered data, we modeled the angular velocity as the nominal angular velocity plus, multiplied 1 plus one term, which is giving a slow drift basically of the a white noise of the angular velocity, so a slow drift in angle. And so we simulate this complex function or noisy function, and here is a noisy is a normal distributed random number for each sample. And so we simulate this, and we assume in the analysis a stable halfway plate. And the impact of that is that what is, for example, a constant polarization in the sky, or a constant polarization coming from the instrument, for example, from instrumental polarization, will not be, it will not appear at a single frequency in the timelines, but will be spread out in frequency in the way that we picture in this figure. You can see here we're simulating a contamination systematic effect at 1 times the frequency of the halfway plate, 2, 3, 4, and 5. And while the black curve is the expected Fourier transform of a noise-free timeline of CMB polarization. I mean CMB signal with intensity appearing here and polarization appearing here. So basically, the fact that we have this noise in the stability of the halfway plate rotation rate will generate, will broaden the line, for example, at exactly the halfway plate spin rate, generating effectively one over F noise appearing after the modulation. This is particular worrisome because this is affecting in particular the large scale. So here, this plot on below is a zoom around 2 hertz of the top figure, and you can see those spikes in the signals. Those are basically the harmonics of the spin rate, in which you see the dipole is appearing here, the quadrupole is appearing here, and so on and so forth. So you can see that this contamination is is spreading to the large scales, the dipole, the quadrupole, the octupole, and so on. And this is, since this is the main objective of Lspe, this is something which we think we should look with great care, for example, also for library. And okay, here is some results. So we have made simulation with different levels of this contamination, and the contamination is removed by notch filters, which is only removing the contamination, but not going as wide as hitting the CMB signal. So we have those notch filters, and then modify the iterative describer to recover the signal. And here we can see, as a function of this output stability, the level of the bias in R. And you can see that after a quite flat region, it starts stepping up very fast. And on the bottom here instead, this is the calibration angular error. So this is a more standard analysis. This is the offset angle of the knowledge of the polarimeters and the output plate. So this sets how well we need to measure the angles. Okay, let me try to conclude. Time is running away. So this is for the component separation. We have used in our simulation, we have used FG Bastel, and you can see here the weights and the data we have combined. We did combine Quixote, Planck, Strip, Planck, all frequencies available, and Swipe, and again Planck. And you can see how much Swipe, in particular the 145 gigahertz channel, how much weight gives into measurement with respect to the other instruments. And here's the estimated EE and BB power spectrum, but our analysis is not based on the power spectra, but is based on a map-based likelihood, which is written here, in which this is the likelihood. The data are in the map here. And the model basically is inserted in the correlation which we have in the map using this simple equation, which we have, the model depending on the cosmological parameters and the noise of the instrument. And here is the result in terms of sensitivity to R. This is on the top, you can see the tensor to scalar ratio posterior probability. And in the case of R equals 0, and in the case of R 3, 10 to the minus 2. And here you can see the sensitivities, in the case of R 0.03 is about 0.01 sigma. So we can detect at 3 sigma, basically, this signal. And if R is 0, we have an upper limit at 95% confidence level of about 0.15. Okay. We also have some simulation for the optical depth tau, which is very interesting, and for anomalies, which are modeled by a modification of the Cosmoglobe scalar power spectrum, and of the birefringence angle, around 0.5 degrees. So let me summarize and conclude. So both Strip and Swipe are in assembly and testing phase. The planning for start of the observation is for Strip the summer 2022, and for Swipe winter 2022-23. Again, the bands are 45, 95 gigahertz for Strip, and 145 to 10 to 45 for Swipe. The coverage is, the common coverage after masking the galaxy is about 25%. The target is to detect R 0.03 at 3 sigma and put an upper limit of 0.015 at 95% confidence level in case of R is below that. And also we measure tau, birefringence, and anomalies. For what concerns the data analysis, we have a joint effort of Strip and Swipe. We have support at the moment by the Italian data analysis community in CMB, and we have support, financial support for running the pipelines on Seneca clusters granted by INFN, and we have instrument simulator deeply developed and in use. We have introduced many systematic effects in the simulators, and of course there are more to introduce. And I think this is a very important point that some of the technology of strip, swipe, and swipe in particular, is very useful for, as a testbed for future satellite missions such as Lightbird, including, in particular the halfway plate impact into volumetric data. And thank you for your attention.